Yeah, see, Jonathan, I don't think that's your computer doing it. I think it's mine. And I don't know.
No, it's telling me. Popped up on my
I think
screen.
it's everyone's.
Really?
Cause
Oh,
mine makes the noise.
huh. I don't know when that started doing that. That must have been a recent Zoom update, but it
Asking me
is.
if I want to leave the meeting because you're recording.
Oh, wow. Okay. Well, somebody probably had some privacy issues or something. And so Zoom had to make some changes to their platform. So, um, we are in geometry, kind of the end of week 8. Next week is finals week. And so the only thing that we really have left to talk about today are circles. Anybody know anything about circles? Like how to find the area or the circumference, or do you even know what those? Do you know what circumference is?
Yeah, I think so.
Okay, try me.
Um, is it the area like between one end and the other end, or is
Well,
it
circle doesn't really have any ends
like in between? I don't know how to explain it.
inside.
Inside, like it's
Yeah,
the whole
yeah,
diameter.
yeah. The area is the same kind of concept, regardless of what shape you're talking about. It's whatever is contained within a two-dimensional shape. I was hoping you were going to tell me about circumference.
I don't know exactly.
Circumference, the analogy for circumference in other shapes is perimeter.
Oh,
Circumference is the distance. If you had to run around the circle, that's how far you would go. That would be the circumference.
I see.
So just like with perimeter of a rectangle, that's the fence around the yard. Circumference is the same thing because it's a different calculation. So the other thing that is different about circles is that now we have to start using an irrational constant called pi. You know about pi?
3.14.
3.14, exactly, right. And pi is an irrational number. They've had, and we were talking about NASA, but NASA scientists have taken pi out to like a million decimal places, and it never repeats it. They've so far, it's never repeated a pattern, or it doesn't end. Um, and pi is actually the relationship between the circumference and the diameter of a circle, and it's a constant no matter how big the circle is. That's why we can use it in all kinds of calculations involving stuff that's round. Um, if you're talking about the area of a circle, it's pi r squared. Okay, well, the joke there is that pies aren't usually square. They come in a round plate or a round baking tin. It's not really a very funny joke, but it's a math joke. But for us, for geometry, pi r squared means we take pi times the radius squared, and that's how we find the area. So already you're hearing maybe some new vocabulary. So that's where I want to start. So right away in this, I guess the good news for this circle handout, it's only 8 pages total, right? And we're not going to be dealing with even with everything that's in here. So this is kind of like the very beginning packet because it starts off with some vocabulary terms and an opportunity to create little drawings. So for sure, you ought to, if you take some good notes on these, any kind of problem that comes up involving circles, you should have no problem dealing with it. A lot of these, though, we're not going to have to worry about central angle, inscribed angle, that sort of thing. We are going to be dealing with these formulas. Our area, just talked about that, pi r squared. circumference is a little different because now it's 2 pi r, or diameter times pi. That's another thing that you got to be careful of when you're talking about circles, is making sure that you know the difference between the diameter and the radius. Anybody want to try what those mean?
Isn't radius half of the diameter, or the other way?
Radius is half the diameter. That's an excellent way to say it too, Jesselyn. Very good. The radius is that point. If you go to the point right in the center of any circle and draw a line to the edge of the circle, that's the radius. And it's going to be the same no matter where you go, where you draw that line in the circle. If you use that same point and you draw a line all the way across the circle, then you have the diameter. So the reason I say you have to be careful to keep those separate is the circumference formula, for instance, can be written as 2 pi r, or pi times the diameter. And if you get those mixed up when you're doing the calculations, you could be off by double what it should be, right? Because 2 times r is the diameter. But if you use the diameter instead of the radius, now you got 2 times the diameter and you've doubled what you should have. So that's just one word of caution. So to start off with the definition, there's your little drawing for radius and for diameter. And the letter P that's being used here is just a sort of labeling for this particular circle, circle P. You could have used anything, circle A, circle B. They're using other letters of the alphabet, though, for points that are on the actual circle. If you think back to the way a line was originally defined at the very beginning of the term, it's a series of points, right? All strung together. You put enough points together, eventually you have a straight line. Circle is kind of the same way, a set of points equidistant from a given point. Well, that given point is the center. And no matter where you go on this circle, every point is the same distance away from the center. And that's what the radius represents. It's that distance from the center point to the edge of the circle. No matter where you draw a line, that radius is going to be the same. If it's not the same, then you don't have a circle. You might have an ellipse, and we don't have to deal with any of these terms this term. You might have seen some of them in Algebra 2, an ellipse or a parabola, other kind of shapes like that. So this is a simplified sort of approach on using the basics here that anybody really should know for using involving circles. Has anybody ever flown out west and seen the big irrigation circles in the farm fields? Okay, apparently not. If you get a chance and have a window seat when you fly out west, you know, if you got a 20-acre plot of ground, a lot of those farmers out there have irrigation systems that are anchored in the center, and they just go around and water their fields in a big circle. So that's one in the real world example of where you might see a circle. And I mean, that farmer's got to figure out how much area he's going to cover, because he's got to estimate you don't want to plant crops in an area that's not going to be irrigated, because then you've wasted your money. You know, how many crops does he need to cover that area? How much water is going to cover the area? So that kind of stuff's important. I don't know if you ever tried to draw a circle yourself with a piece of string. Maybe when you were younger, maybe even in an art class, you might have taken a string and pinned it on a piece of cardboard and put a pencil on the outside of the string and went around and around and around. Eventually, you're going to get a circle. I don't know why I was thinking of those examples, but that's what came to mind. A chord, don't worry about a chord. It's just a segment with any two endpoints somewhere on the circle. Secant and tangent, we won't see that very much. This is kind of, hopefully it's not too confusing with what we just did with right triangles, because those words are also used sometimes involving, obviously tangent is with right triangles, but your tangent's got a different meaning when we're talking about circles. If you've ever heard somebody, and it's used in a lot of common language, if you ever heard somebody say they flew off on a tangent when they're talking about something, this example here of a line that barely touches the circle is what that really means. If you've ever and maybe this is a guy thing, but if you have something that's on a string and you're kind of winding it up, you're spinning it around in your hand above your head, and you let go of that, the direction that thing takes off from that circle it was orbiting in, that's the tangent. So it's just gonna
like a lasso.
Yeah, it's kind of what they do with you know, if something's going to break out of Earth's orbit, you know, it's got to go off on some kind of tangent from its orbit. It may not be a straight line, but it's only, you know, that's the sort of departure point for whatever. So then you have this point of tangency. It's just the one point that actually touches the circle. Probably going to see more with arcs than any of these other things, because the arc allows you to start measuring how much of a circle is actually getting used. A minor arc, just because it's less than 180 degrees, and you got some symbolism here. You're going to use two letters with a little half circle line above it to represent that that's an arc. But if you end up taking more of the circle, then more than 180, now you have a major arc, and you got to use three letters. Because if you just say AB, that's got to be clear that it's only this small part of the circle, not going the other way around from A through C to B. It's just directly from A to B. So that's why they have a major arc designated with three letters instead of two. Semicircle, always 180. And here is another representation that matches up with our definitions for supplementary, straight angle, linear pair, right? All those things equal 180, because if you cut a circle exactly in half, that's what you get. That's half of 360 degrees. A circle, the number of degrees in a circle is always 360 degrees. So half of it, when you cut it with the diameter, half of it's going to be 180. So these three formulas, make sure you get these written down. You're going to need them. Now, there's no test for this unit, for the circles unit, but you can expect to see at least one problem on the final involving circles. And it's probably going to be one of these three formulas. Here's what I was talking about before with circumference. 2 pi r, or pi times d. Make sure you use the right one. The arc length is like a part of the circumference, because now you're trying to find how far around this circle you're traveling from one point through another to an ending point. Anybody have questions over any of those? Anybody need more time to make some notes? All right. So if you go to page 4 here, the thing about this packet is it gives you a pretty good indication of the things that you need to be concerned about with circles. So what does it start off with? Well, this previous page, page 3, is just a different way to identify the vocabulary, right? The center, that's obviously P on this circle and X on the other one. The radius is XY or XR, QP or PN, okay? Tangent, even tangents down here, tangent to both of those circles. It crosses and touches each one only at one point. And the point of tangency is right there, letter R. So all they're doing on that page is reinforcing the definitions from the first couple of pages. So I'm not going to spend any time on that. That's something that you guys can work on. If you have questions about that, I'll be happy to help you. So the first set of problems here says find the area for circles 1 through 4 and the circumference for circles 5 through 8. Okay. So what's our equation going to be for problem number 1? Well, we're talking about area. So we're going to be using pi r squared. So we're going to use pi times 12 times 12. 12, the radius is 12. The square of 12, 12 to the second power is 12 times 12. So 144 times 3.14.
452.16.
Okay. There might even be, yeah, on my scientific calendar, there's actually the constant pi. So let me see what happens. Pi times 144. What did you get, Jonathan? What was the answer that you got?
I can't remember. I closed it out.
Okay.
3.1 times 12. 452.16.
Okay. 452.16. Well, when I use the constant pi that's built into my calculator, I got 452.389. Why would I get a slightly higher number than what Jonathan got?
Is this one rounded?
Well, when you use 3.14, it is the rounded version of pi, yes. And that's only to 2 places, right? I have no idea how many decimal places the built-in constant of pi are included in my calculator. But it's pretty obvious, I would think, that if you for a little computer like this calculator, it could be 10, 15, 20, maybe 100 decimal places. Well, that means it's more accurate. It's more precise. And so you got more numbers to multiply. So naturally it's going to be a little bit larger, but it's not by much. It's no big deal. Use 3.14. I mean, that's probably the most common sort of abbreviated form of pi that everyone accepts. What about problem number 2? How would we set that one up? We're still talking about area.
So you just take half of 18.
Half of 18, and this is one of those problems where I'm just cautioning you about. Don't just take pi times 18 squared, because 18 is the diameter. It's not the radius. You got to be sure that you keep those separate, those definitions separate in your mind, because the correct answer for number 2 is going to be pi times 9 squared, not pi times 18 squared. That's a huge difference. In fact, it's going to be more than, I'm just curious. I know 9 squared is 81. So what's 18 squared? Okay, 324. So it's 4 times as much. You're going to be off by a power of 4 if you use the diameter instead of the radius. So be sure you pay attention to that. Same kind of thing is going to apply when you're doing these 5, 6, 7, and 8 problems. Because remember, what's our equation? 2 pi r, or pi times the diameter. Okay. 5 and 6, we got the radius. So we're going to have to multiply these numbers by 2. 2 times 7 times pi. That's going to give us the circumference. 7 and 8, though, we don't have to multiply these by 2 because we have the diameter. Because the diameter is 2 times the radius. That's why they write the equation slightly different, because it kind of depends on what information that you're given. Questions so far?
No.
Now, there's only so many things that they can do with these area and circumference problems. So you can see right away, problem number 9 and 10, they're trying to turn the use of these equations around on you. Find the diameter of a circle with a circumference of 65.97 meters. We got the circumference, and it's asking us to find the diameter. How do we do that? Are we using the same formula?
Yeah.
Yeah. In this case, they gave us the diameter, so I would set this up circumference equals pi times the diameter. Okay. So what's the circumference? What was the number that they gave?
67.59 or something. I don't remember.
Yeah, let me go back and look at it. $65.97. Okay. And these are not complex problems at all because we know the circumference, so you just plug it in. 65.97 equals pi times the diameter. Okay, we know what pi is, right? So we can erase that and plug in 3.14 times the diameter. So now it's just a one variable equation at that point, because since pi is a constant, we can always replace it with the actual numbers that we know. So solving for D in this case is easy. We're going to divide both sides by pi, 3.14. $65.97 divided by 3.14. 21.00955, etc., etc. So it's basically 21. The diameter is essentially 21. Because I didn't see if it tells us, what does it tell us to round to? Most of these will be like that because it doesn't say round to any particular decimal. But if you're using 3.14 as your pi number, then you probably need to round to the nearest hundredth place, because pi, you're using pi rounded to the hundredth. Well, that answer I just got was 21.00, so we don't have to do anything more. So I'm going to pause this here and give you guys a chance to do problem number 10, finding the radius of a circle with an area of 380.13 square inches. And it's essentially doing the same thing as I did on the other one, only now we're using the area formula instead of the circumference formula. And go back to my whiteboard. Now I'm talking about area equals pi r squared. So I know what the area is. .13. That's 1 equals pi times the radius squared, and the problem is to find the radius. Okay, those terms on the right-hand side are multiplication. I need to get the r by itself, so I need to divide both sides by pi. I get 121.06, and that equals r squared. But I still don't have the radius yet. How do I get the radius when the term that I'm looking at in the problem says it's r to the second power? What's the operation we have to use now to undo a square?
Dang it.
It's a square root. This is you have to do the same thing on this as we did on those Pythagorean theory problems. When we're trying to get to C, remember, if we're trying to find the hypotenuse or any of the other terms, a squared, b squared, or c squared, how do you undo a square? You use a square root. So I square root both sides. I'm going to get R, and the answer is going to be 11 point something, because I know 11 times 11 is 121. 121 is one of those perfect squares. But because pi is involved, we're never, ever going to get a number that comes out exactly even. 11.0027269347194107305, on and on and on. And that's what happens when you deal with an irrational number. Irrational numbers never end. They don't repeat, they never end. And that's what pi is. It's an irrational number. And if you need help remembering that, think about it being a crazy number. Crazy people are often irrational. All right, any questions about how to do that kind of an area problem when you're basically just taking the information and plugging it into the formula? Central angles, arc measures. Central angles, we like central angles because they go to the very center of the circle. The degree of the arc is going to be the same as the degree of the angle. If you look at problem number 1 here, we got these two lines that cross through the center. Can you figure out what arc ML might be just from that drawing?
Yeah, because they're the same.
Yeah, exactly. Vertical angles. Heck yeah. We already know about vertical angles. Anytime two lines cross, it doesn't matter that it's inside the middle of a circle. It's still the same relationship between the sides of the intersection there. 21 on the top, 21 on the bottom. So if you subtract 42 from 360, that's what's left on all the rest of, if you take L and K and J and M, that's the remaining part. And that's what they're asking you to figure out. So it has to be split. So 360 is the total degrees minus 42 from those two angles. That leaves us with 318 degrees in total that's left for this central angle over here and for this central angle over here that has to be split between those two. Nothing to indicate that one's larger or smaller than the other. So what's 318 divided by 2? 159 degrees. So J and M, 159. JKM is going to be 159 plus 21 plus 21. KL, that's 159 because it's the same as the central angle. So let's see if I'm right. Okay, gotta find it. Again, this packet doesn't match what you guys have. Here we go. All right, there we go. Yep, 159. JKM. See, what did I say? These two total 42, so 159 plus 42, 201. Yep. MKL goes the other way. It's everything except for that 21 degrees there that's in that ML arc. Okay. So if you look at how these notes here are written out, let me see the best way to maybe describe this. When we were doing parallel lines and transversals, and we were trying to figure out angle measures based on whether or not something was, you know, alternate interior or alternate exterior or any of those relationships. Figuring out these arc measurements is kind of similar to that, because you know the total is going to be 360, right? We're talking about a circle, so that's a given. That's a good thing. So if you look at problem number 2 here, where did some of these numbers come from? Got 72 and 87. This line here, WU, looks like it's the diameter, because it goes all the way across the circle. SV also looks like the diameter. So there's 180 degrees here from W around to U. There's also 180 degrees from S around to V. So now you can start carving this thing up. We got another 2, actually, well, 1 vertical angle situation between here is 72 degrees and this side over here, UV, also 72 degrees, UXV. So how much is ST? Well, if we take 72 and 87, add those together, that's 159. And so what's left out of 180 is this ST arc, and there it is, 21 degrees. So finding these arc measurements is basically like finding pieces of a puzzle. And the good news is that it all's got to come out of 360 degrees. And when you have these diameter lines crossing through here also, you know you're dealing with half, 180 degrees. So now we know this is 21, this is 87, and this is 72. That's 72. So we could figure out what's remaining here in this WXV piece, or any of the others. TVW, where's that? TVW, that's a major arc. All of this except for the 72, except for the 21. Questions? The strangest word on this page is right here. Radii. You know what radii refers to? What it means? It's the plural of radius. This first problem, there are 4 different radii that are shown. Because if I go to the center here and then straight out to the edge of the circle, there's 1 radii, NJ, NK is another, NL is another, NM is another. That's where the word radii comes from. You can have multiple radii over radii. In number 2, we got WX, we got SX, we got TX, we got UX, we got VX. Those are all radii. Half of the circle, half the distance across the circle through the center. Strange word, but it's necessary. And of course, you know, what are they going to do now to try to make it more complicated? They're going to add some stuff in here that looks like algebra. Yeah, big deal. Doesn't change how you're going to solve one of these problems. It still all has to relate to 360 degrees at some level. in this case here, and number 5, are we going to use 360 in our setup? Or are we going to use 180? That's a good problem here. I'm gonna copy and paste that one into something I can work with and do a little quick demonstration here. So if I'm trying to figure out what X is, let's say for a minute that I'm not really sure if that line right there, RT, makes a semicircle. If it really truly cuts that circle in half, I don't know. I'm not positive. So to be conservative, I probably should not assume that it is. But how much is this angle over here?
26.
It's a huh?
26.
26. Yeah, it's another one of these vertical angle situations. So I know that piece is 26 degrees. So how about this one? Another vertical angle situation, right? So I don't know how many degrees that is, but I got a description here. It's in algebraic form. It's an expression. So what? We know how to deal with those. So I've got 2 angles that are 26 and 2 angles that are 15x minus 26. And that covers everything for the whole circle. So now I'm working with a total of 360 degrees, right? So how would I set that up as an equation?
You do 15x, or yeah, 2 times 15x minus 26 plus, what is that, 12, 52.
Okay. You went ahead and did the multiplication. I'm going to show it broken down as 2 times 26. So your 52 number is correct. And all that's got to equal 360. That covers every angle that is shown inside that circle. So 30x minus, and you're just not going to believe how easy this comes out. You should already be seeing the answer. My 52s cancel. I got 30x equals 360. Divide both sides by 30. I think that's 12. Yeah, if I chop a 0 off of both of those, I got 360 divided by 3. X equals 12. And any kind of problem that you see like this is essentially solvable in the same manner. And I know you've heard me say before that a lot of times, especially involving geometry, we can't assume things. And so that's the most conservative approach that I took there, was to make sure I included everything that I absolutely knew about because of the other definitions that we've already learned, right? And the only one that I used on this problem 5 was vertical angles. We've been working with vertical angles since day 1. So if you're still struggling with those definitions from the first day of class, go back and watch that video again and get all those notes filled out, because that stuff comes up repeatedly, almost every lesson, almost every test. Okay, then the only other thing that they're going to try to show you here is how to figure out the length of an arc. if you've got to put a fence around a circular object, you know, and where this comes into play a lot is not so much in fencing, but in construction. Because if you're building a building that's got curves in it, you got to know how much material is required. What's the length of that material in order to build the building correctly? If you're pouring curbs, you know, pouring concrete and making curbs in the street, how much material is it going to require for a specified arc? You know, most of those type of things are a lot of them actually are set up in standards that the government sets. So if you can do the basic calculations, you're not going to overestimate, you're not going to underestimate. If you overestimate your materials, you've spent money as a contractor you didn't need to spend, and your boss is probably not going to be happy. If you underestimate, then your project's probably going to get delayed, and your boss is again not going to be happy because now you got to order the materials, some more materials, and everybody's standing around waiting for the concrete truck. It happens. So don't let it happen to you. So these are simple calculations also. You're going to take the measure of the arc, which is just the degree measurement, and to find the length, you divide by 2 times pi times r. Using that arc length formula. Right? And what they start off with in the formula is C for circumference. And here's a little reminder. Circumference is actually broken down into another formula itself. Questions, anybody, on any of those kind of problems? And that's pretty much it for this whole packet. I wouldn't worry too much about these inscribed angles and that sort of stuff. It's here, but it's not really tested. So what I'm shifting to now is the final exam review. Pretty sure I posted this in Google Classroom. This, I would recommend that you go through this handout and do these problems. It's probably going to be the best way for you to be prepared for the final. The final is only 10 questions. So what I tried to do in setting up the final was, you know, for certain, one question about every unit. We had 6 tests. We have 7 units. So there's going to be at least 7 questions, one from each unit, that are kind of representative. And then 3 others are added in there that are to sort of help emphasize something that I thought was especially important. So you can count on having a trig problem. You know, problem number 2, what kind of problem is that? What are you going to use to solve that problem? The ladder against the wall problem. It's not trigonometry. How are you going to figure out how far the ladder is from the wall? You're going to make a drawing?
Yeah.
I hope so. Because if you do, the solution should become obvious. 17-foot ladder. We got a wall here. You got to assume that the wall is at a right angle to the ground, right? I mean, it's part of a building or it's something. It's not going to be leaning. The ladder goes up to a spot 15 feet high on the wall. So what formula or what calculation are you going to use to figure out this distance? It's not asking about angle measures, so you don't have to worry about trig.
Distance formula.
I would agree with you if this were something that had ordered pairs and was plotted out on a graph. But what's the distance formula based on? Where does it come from?
Slope intercept.
No. Who's the guy? Starts with a P.
Oh, theorem.
What?
Pythagorean theorem.
Yes.
However you say it.
Pythagorean theory. Pythagoras. And what is the Pythagorean theory?
A squared plus B squared equals C squared.
Right. If you don't know the Pythagorean theory, you cannot do geometry. I'm just telling you that right now. It's one of the most basic functions of geometry. It's 3,000. It's been around for 3,000 years. So where do I put these numbers now that I've got the right theory figured out? The shortest side, I almost always say, is A. The hypotenuse is always C. Jonathan and I were talking about that yesterday with some trig stuff because it's true with every right triangle. The hypotenuse is always C. It's always opposite the right angle. So you can count on that. You know that as a fact. So I can use 17 here instead of C, which leaves my middle side as B. Now you just solve for X. 15 squared is 225. I don't know what 17 squared is. 289. Subtract 225 from 289. I bet you this comes out even. X squared equals 64. X equals 8. So the ladder, the base of the ladder is 8 feet away from the wall. How did I get that? Last step, like we were talking before, square root the square, cancels it out. So in order to help you get ready for the final, and I'll double check as soon as we're done here, but I'm pretty sure I posted this in your materials. Ooh, trig ratio for the tangent of A. Okay. What are the sides that we're dealing with for the tangent of A? Remember, tangent's the only one that does not involve the hypotenuse. This is TOA. Opposite over adjacent. Opposites here.
8 over 15.
8 over 15. There you go. That's it. That's the trig ratio for the tangent of A. It doesn't even ask you to calculate or do anything else with it. You got it now, Jonathan. Got some scale problems here. Got some similarity stuff. Remember, similarity is not the same as congruence. We're going to have the same shapes, but different sizes, and we got to deal with a scale factor. And normally we do that using proportions, right? And we can use these similarity statements. That gives us the corresponding sides. There's a congruence, triangle congruence question. What additional information is needed to prove these triangles are congruent? Well, I got one angle here, I got an angle here, I got a side here, I got a side here. So for angle, side, angle, I need to know what angle B is or angle Y. I need to know those two angles, angle, side, angle, angle, side, angle. For side, angle, side, I need to know what AC is and what that XZ is congruent, because then I have side, angle, side. Remember the congruency stuff, you just go around the triangle. However, whatever the lettering order is, that's what you have to find in order to know that two things are congruent. Angle, angle, side, I need to know that angle C and angle Z are congruent. So it's different for each one of those proofs. So if you want to go through the study guide, and then if you need help on any of the specific problems before you take the final, you can text me, or just come to the Zoom on Tuesday, and we'll go through any of those that anybody has a question about. Because the circle stuff today, that's the last piece of new information. So right now it's all about getting all those unit tests done. There are also a couple of additional homework assignments that are Google Forms that I've included to help get you ready for the final. I think they're 10 or 20 points a piece. So that might help bring your grade up and also help you see the kind of problems that you can expect to see on the final. So, questions, anybody?
Not yet.
Okay. Well, for the next few days at least, we'll probably have to be communicating by text and not so much by Zoom. But if you need help, I know it's the weekend and the holiday and all that stuff. Don't wait till Tuesday if you're stuck. All right? Because if you wait until Tuesday, now you only got Tuesday, Wednesday, and Thursday to get this stuff done. And you've wasted 4 days. You still got Friday, Saturday, Sunday, Monday, plus the rest of today. So I'll get back to you. It may not be immediately, but I will get back to you if you text me. Promise you that. Okay, everybody? All right, Jonathan. Thanks for keeping your camera on and participating, and for all you guys for being here today. Have a good weekend.
You too.
And I'll talk to everybody soon.